Hello, I'm Notion Afroz, and today's my topic of presentation is scaling theory below 20 nanometers. So, general scaling trends in MOSFETs. According to Moore's law given in 1965, transistor per chip will increase by a factor of 2 every 18 months with a goal to decrease the cost per transistor and reduce the power consumption per component. And this was achieved by a combination of scaling component size and increasing chip area. So if we look at the figure below, we can see that from starting from 1970s to 2020s, there is a linear increase in the transistor density per chip, and it maintains Moore's law by increasing by doubling the transistor density every 2 years. So in 1974, Robert Dennard proposed a scaling theory where he scaled the length, width, and oxide thickness by a factor of 1 by k and scaled the doping concentration by a factor of k, and which in turn scaled the depletion width by a factor of 1 by k. So as a result of scaling the MOSFETs according to Dennard's scaling theory, it resulted in high performance transistors providing higher drive current and lower parasitic capacitances. And it continued until 130 nanometer transistors in the thousands. So uh, basically over the last 20 years, the minimum feature size decrease per every 2 years of the transistor is 0.7 times, which we can see from this graph, and that resulted in 0.5 times area scaling and thus maintaining doubling transistor density every 2 years. But 14 nanometer and 10 nanometer technology took longer than 2 years due to increased process complexity, but it was still able to maintain Moore's law because there was a significant increase in transistor density. So basically, scaling the MOSFETs according to Dennard's scaling theory was not possible below 130 nanometer technology because the gate oxide thickness was already reduced down to 1.2 nanometers, and scaling it further below would result in significant increase in leakage current. So changes in uh, scaling trends occurred to reduce the leakage current, and Intel in its 90 nanometer technology adopted strain silicon transistor technology. And so basically there tensile strain in NMOS transistor channels were applied to increase electron mobility, and compressive strain in PMOS transistor channels were applied to increase hole mobility, and they together increase the transistor drive current without having to further scale the silicon dioxide gate thickness. So this was adopted by all the semiconductor companies and is still in use in the 10 nanometer technologies. So another improvement in MOSFET technologies was done by introduction of high-K gate dielectrics, and Intel first adopted it in its 45 nanometer technology in 2007. So basically, the traditional polysilicon gate electrode was replaced by metal electrode with separate metals for NMOS and PMOS to provide optimal transistor threshold voltages. And this resulted in significant improvement in transistor performance and reduced transistor leakage current and improved transistor drive current. And this technology is also was later adopted by all the advanced logic and with the introduction of high-K dielectrics, the further improvements in MOSFET technologies basically slowed down. So it was a big challenge to scale the MOSFET below 32 nanometer technology become a big challenge because of the short channel effects it was showing, including high leakage current, threshold voltage roll-off, drain-induced barrier lowering, velocity saturation, mobility degradation. And to overcome the short channel effects, several new transistor architectures have been proposed till date, including carbon nanotube, nanowire FETs, FinFETs, and scalloped FinFETs, group 3, 5 component-based devices, graphene nanoribbon devices, etc. And amongst all of them, FinFET technology was adopted by the semiconductor companies below 22 nanometer because it showed superior performance along with its ease of fabrication uh, using the existing fabrication methods. So FinFET is basically a multi-gate device which has gate all around. It's a channel and FinFETs come basically in two forms, bulk FinFET and SOI FinFET. So these are the two basic FinFET structures. In the SOI FinFET, the fin is completely separated from the substrate by this oxide layer. So basically in a 3D FinFET structure, the gate electrode has better electrostatic control of the transistor channel formed, and thus this improves the electrostatic control, and it results in a steeper subthreshold slope of transistors, resulting in short channel effects reduction, like subthreshold voltage, drain-induced barrier lowering, etc., and all the others. And also it increases drive current at higher current density and improve performance at low operating voltage. So there are basically two types of FinFETs, double-gate FinFET and tri-gate FinFET. And we can see from the figure here that the gate the gate, there is a vast difference between the gate and the channel. And figure A, due to the thicker oxide layer, and thus the upper gate does not have that much control over the channel. And so this is a double gate FinFET, while in figure B, we can see that the oxide layer between the gate and the channel is small. So the gate has a greater effect and it can control the channel. So this is a tri-gate FinFET. Also, there is two modes of operation of FinFET, short gate mode and independent gate mode. So the number of gates that control the conduction channel could depend on the modes of operation, and the front and rear gate terminals are shortened in short gate mode. In independent gate mode, the gate terminal is disconnected and two gates control the channel. Okay, so here. So if we compare between FinFET and MOSFETs, so if we compare between FinFETs and MOSFETs, what we can see is that in FinFET there is a reduction in leakage current. Also, the FinFET is 37% faster than a 22 nanometer FinFET is 37% faster than a 32 nanometer planar MOSFET. So basically, here it is presented a table of the performance comparison between 7-nanometer FinFET and conventional bulk CMOS based on the performance of standard cell libraries. And from here, we achieve the following conclusions. So for super threshold supply voltage and normal threshold voltage, so the super threshold supply voltage is the 0.30 volts, and uh, yeah, so here in case of 7-nanometer FinFET shows to be 3 times and 15 times faster than its 14-nanometer and 45-nanometer CMOS circuits. And also 5 times and 600 times, there is a 5 times and 600 times reduction in average energy than in 14-nanometer and 45-nanometer CMOS circuits. So it was for a near threshold supply voltage and normal threshold voltage. The 7-nanometer FinFET shows 7 times faster speed than 45-nanometer CMOS circuits, and it shows a 7 times reduction in average energy than a 14-nanometer CMOS circuit. So basically, 7-nanometer FinFET drastically improves the speed and energy and reduces energy than a conventional bulk MOSFET, and along with reducing the short channel effects and short channel effects. So here, if we see a comparison between 14-nanometer and 10-nanometer Intel technology, we can see that in 14-nanometer Intel technology, there is a 0.3 times area reduction than in its 22-nanometer technology. And in 10-nanometer technology, there is a 0.37 times better logic area scaling than its 14-nanometer technology. So area-wise, the Intel's 10-nanometer technology is much better than the 14-nanometer technology. Also, if we see in case of 60 RAM bit cell area, so in case of 14-nanometer technology, it is 0.0588 millimeter per square, and for its 10-nanometer technology, it is only 0.0312 millimeter per square. So there is a vast improvement in the area of 60 RAM cells in Intel's 10-nanometer technology than its 14-nanometer technology. Also, its performance, transistor performance has been increasing in a logarithmic scale with its decrease in technology node. So if we compare between different the technological nodes given by different foundry process, we can see that here we can see for Intel, Global Foundry, Samsung, TSMC, etc. So they so basically in 2000. Intel gave its 14-nanometer FinFET in 2004, between 2014 to 15, and so if we come here to 2019 and the recent years, we can see that Intel is still in its 10-nanometer technology, while TSMC has reached 7-nanometer technology, and Global Foundries also reached 7-nanometer technology in 2018, but it is also working on its 12-nanometer FDSOI technology. Also, Samsung reached its 7-nanometer technology in 2018, and it's working on its 18-nanometer FDSOI technology. So from here, we might think that Intel has not yet released its 7-nanometer technology, whereas Global Foundries, Samsung, TSMC has reached 7-nanometer technology further far before Intel. But if we compare, but the transistor density is much more important than transistor size nowadays, because smaller transistor size actually not always mean that their is an increase in transistor density. So from this table here, we can see that the transistor density for Intel's 10 nanometer technology is more or less similar to the TSMC's and Samsung 7 nanometer technology. Though Intel's 10 nanometer, though Intel could not still reach 7 nanometer technology, but according to transistor density, Intel's 10 nanometer technology just provides chip with the same density as TSMC's and Samsung 7 nanometer technology. So basically, this graph represents the roadmap of transistor scaling for Intel and the TSMC and Samsung over the years from 28 nanometer to 7 nanometer technology. And from here also, we can see that Intel's 7 nanometer technology shows to give the highest transistor density with its 10 nanometer node than the TSMC and Samsung's 7 nanometer technology. So basically, FinFET there are limitations of scaling FinFETs further behind the limit. The minimal switching energy for a realistic FinFET is 100 kBt, and FinFETs are already approaching near to that value at its 10 nanometer node, and further increasing further decrease in FinFET technology might result in increased thermal fluctuations and consequent logic errors. So ITRS has projected that by the year of 2030, the further downscaling of FinFETs might not be possible, maintaining its performance. Research has been being conducted for alternative technologies to replace FinFET to scale the transistors further below to maintain Moore's law in the future. So basically, horizontal gate all around thin field effect transistors such as nanowire, NW FET, and nanosheet FET has better performance electrostatics than FinFET, and thus can be considered as promising options for continued scaling. So if we compare the performance of FinFET and gate all around FETs, yeah, and from a paper, it was taken that if we simulate FinFET and get gate all around FETs with TCAD at VDD of 0.7 volts at regular threshold voltage, then gate all around FinFETs has improved DIBL performance than FinFETs. Also, it has reduced threshold voltage roll-off, and it also reduces the sub-threshold slope by 13 to 29%, which is a very great improvement. Thus, from these results, it can be said that gate all-around FinFETs are suitable to replace FinFETs only if it can be fabricated. It can meet the fabrication challenges. Gate all-around FinFET in comparison to FinFETs give higher drive strength and also improve the leakage performance. So other potential replacement of FinFETs can be MOSFETs with group 3 to 5 semiconductor channel materials because they show higher mobility than FinFETs, and they can provide higher drive current and higher performance to allow MOSFETs to be operated at lower voltage for lower active power. So basically, tunneling field effect transistor is one of such semiconductor material, and could be an alternative for transistors option that operates differently than a MOSFET. The TFET can achieve subthreshold swings smaller than 60 millivolt per decade, resulting in a steeper current turn on, and can therefore operate at a lower power supply voltage than MOSFETs. And also it gives 3 times greater energy delay product than MOSFETs. From this figure, we can see the drive current versus gate voltage electric characteristics of FinFET with TFETs. And so in conclusion, we can say that and now at present, research is being conducted for more energy efficient circuits on CMOS to support the continuation of Moore's law. But though MOSFETs and FinFETs has reached its or is about to reach its maximum scaling limit, but so research for beyond CMOS technologies is being conducted, but these beyond CMOS technologies are not meant to replace the existing CMOS technologies. Rather, there are the research is mainly focusing on developing technology that can be integrated onto CMOS technologies, existing CMOS technologies, and others. Technologies like quantum nanoelectronics and nano magnetics are being the main focus of the researchers nowadays, and to be able to further scale down the transistors even when the FinFETs reach its maximum scaling limit, which was predicted to be by 2030. And if this active research on beyond CMOS technologies is going to be is going to keep the Moore's law alive. So thank you. This is from my side. This is all from my side.